Alright, this video we're going to have a look at the atmosphere. So just to remind you, the atmosphere is this blanket of gases that surrounds the Earth. And you need to know exactly what gases are in the atmosphere today, but also back when the atmosphere was first formed billions of years ago. So we take a look at what was there billions of years ago. Okay, you had mostly carbon dioxide. All of the water was present as water vapor, so H2O was a gas, and you had little to no oxygen. And if you compare that with what we've got today, it's very different. Now we've got mostly nitrogen, so 78% is nitrogen. We've got 21% oxygen, so compared to having no oxygen, now we've got 21%. The carbon dioxide, it's gone from being mostly carbon dioxide down to less than 1% carbon dioxide. And we also have this gas here, argon, in small amounts. So argon is one of your noble gases. You find it in group 0. You need to know these 4 gases in order. Now, if you add the percentages, you'll see they don't actually add up to 100. There's a small amount of other gases, but these are the 4 that you need to know, and you need to know them in order. So let's go back to the early atmosphere. First of all, how do we know that it was mostly CO2? All right, if it was billions of years ago, how are we supposed to know that? Well, we know that the early Earth's atmosphere was made from volcanoes. There was a lot of volcanoes on Earth, and volcanoes emit a huge amount of CO2. We also know that the early Earth was very, very hot, greater than 100 degrees Celsius, and water above 100 degrees Celsius is always going to be present as a gas and not as a liquid. How do we know there was no O2? Well, the earliest rocks, so rocks will contain some iron, and the iron in rocks will react with the O2 in the atmosphere if O2 is present, and that will go from iron to iron oxide. But the earliest rocks don't contain any iron oxide. They contain iron sulfides, telling us there was some sulfur in the atmosphere, but no iron oxides. That means there was no oxygen available for the iron to react with. How has it changed? How have we gone from mostly CO2 to hardly any CO2? The answer there is that the Earth cools down. All right, so the Earth cools, and when it cools, that water vapor was able to condense. So if you've got steam or water in the gaseous form, as soon as you cool it, it will condense and it will form liquid water. In other words, it rained. All right, and it rained a lot. And when it rained, you were able to form oceans and seas and rivers. All right, so on the early Earth, you didn't have any water as a liquid. Now you've got all of these bodies of water, and the carbon dioxide in the atmosphere was able to dissolve in the ocean. So just from the Earth cooling, you get a massive decrease in the water vapor, and you also get a massive decrease in the CO2 as a gas. Because the Earth cooled and we now have water, conditions for living things becomes more favorable. So we have our first photosynthesizing organisms. Now, before plants, you would have just had bacteria, but they can also carry out some photosynthesis. And from biology, you should know that when you carry out photosynthesis, CO2 gets used up, so you're taking even more CO2 from the atmosphere, and then our oxygen is going to be produced. Other thing we need to have a look at is, I've told you that there's 21% oxygen. How exactly do we know that? So you're going to get a few questions using a kind of apparatus like this. So what I've got here is I've got a little bit of zinc in this kind of capillary tube, in this glass tube, and on either side of my glass tube I've got a syringe. So syringe A has dry air. Now we're talking modern atmosphere here, so in that dry air you're going to have mostly nitrogen, you're going to have some oxygen, only a tiny amount of carbon dioxide, and then a little bit of argon, which is unreactive anyway. The fact that it's dry means there's no water in that air, so it's literally just nitrogen and oxygen, and my nitrogen is very, very unreactive. And what I'm going to do is I'm just going to push the plunger of the syringe, and that's going to force this dry air over the piece of zinc. Now, if I do that without heating it, nothing's going to happen. So the first thing I'm going to do here is I'm going to add some sort of Bunsen burner so that I can heat. All right, so I push my syringe in. The dry air moves over the zinc, and as it passes over the zinc will react with the oxygen and air. It won't react with the nitrogen, it's too unreactive, but it will react with the oxygen. So let's say here that we stop started with 50 centimeters cubed of dry air. It's a gas, so we use volume, and that means I'm using centimeters cubed as my unit. So I'm starting with 50 centimeters cubed. When I push it over here, it will pass over the zinc into syringe B, but maybe in syringe B I only have 49 centimeters cubed because the oxygen that has reacted with the zinc is taken out of the air. And then I take my 49 centimeters cubed and I push it back over the zinc, and then maybe over here I've got 47, and then I keep pushing it back and forth and back and forth, and the oxygen keeps reacting with the zinc and it keeps being removed from the air, so the volume in the syringe gets less and less each time, and I keep doing that until the volume stops changing. So let's say we started with 50 centimeters cubed, and then at the end I end up with only 40 centimeters cubed after I keep passing back, forth. That means that in total 10 centimeters cubed of my dry air must have been oxygen. So to get that as a percentage, all right, I take my 10, which is what we know as oxygen, over my starting volume, which is 50, 10 over 50, I times it by 100, and I work out that it's 20%. Now you can't just memorize that number. If you're asked for a calculation, you will have to actually do a calculation. So you'll be either asked to do a calculation or you'll be asked to describe this method. The other little thing we need to look at in this chapter is the greenhouse effect. So we said that there is only 0.04% carbon dioxide, but it is still having a negative effect. All right, so you've got CO2, you've also got H2O as a gas, so water vapor, and you've got methane. And these guys are known as the greenhouse gases, and they contribute to the greenhouse effect. So what this is I've got my sun here, and I've got my earth, and I've got my earth, these dashed lines represent the atmosphere, and the sun heats the earth. Coming out of the sun, you are going to have what we call UV radiation, okay, which is a good thing, all right? It passes through the earth's atmosphere and it heats the earth, and it keeps the earth at a temperature that we can all live on. Some of that UV radiation gets absorbed by the earth, some of it gets re-emitted, and when it gets re-emitted, instead of being re-emitted as UV, it gets re-emitted as infrared, as IR radiation. Now some of that infrared radiation will just pass straight back out through the atmosphere and off out into outer space, but some of that infrared radiation will get trapped, okay, by the atmosphere and then sent back towards the earth again, and this is called the greenhouse effect. And the greenhouse effect is a good thing. If there was no greenhouse effect, if all of that heat energy was able to escape, the earth would be way too cold. So we do need some of that heat energy to get trapped and sent back to earth. But the issue is, if we increase the level of these greenhouse gases, and these are the gases that are able to trap that infrared radiation, if we keep increasing these gases, then the earth is getting hotter than it should. So it's called climate change. Our average climate is changing because of the presence of these gases in the atmosphere.